Good morning, sir. My name is Purnima. Now I am going to give a seminar on natural deduction under the guidance of Srinath sir. This is the agenda. This is the agenda. Now I am going to give a cover. Introduction, declarative sentences, natural deduction, rules for natural deduction, and derivative rules. The aim of the logic in a computer science is to develop a languages to model the situation we encounter as a computer science professionals in such a way that we can reason about them formally. Examples of a declarative sentences are: the sum of the natural numbers 3 and 5 is equal to 8. Jenny reacted violently to the Jock's accusation. Every even natural numbers is greater than 2 is the sum of two prime numbers. Here, these sentences are the declarative sentences because they are in the principle capable of being declared true or a false. In example 1, it can be tested by appealing to the basic facts about the arithmetic. In the sentence 2, it is a bit more problematic because in order to give the truth value, we need to know who is Jane and Jack. They are perhaps to have a reliable account from someone who witnessed the situation described. In the sentence 3, it's a fact about all even numbers which is greater than 2 is either a true or false. But to this day, nobody knows whether the sentence, the example third, express the truth or not. Some of the examples of a non-declarative sentences. Here, primarily we are examples of non-declarative sentences are: could you please pass me the salt? Ready, steady, go. May fortune come your way. Here, in a example one, could you please pass me the salt? Here, it's an requesting, so it's not a declarative one. Ready, steady, go. Just it's an exclamatory sentence. Means we are exciting something. So then only we are telling the sentences. So this is not a declarative sentences. Syntax of a propositional logic. The symbol of the logics here we are using in a declarative science. Some propositional logics are some constants about tautology and a contradiction symbol. The first symbol here we are focusing on contradiction symbol. Here, contradiction means suppose we have one expression. We are going to prove that in all situation that particular expression going to give an false value, so that we can conclude it as a contradiction of that expression. This one is a tautology symbol. Here, for some given expression, we are going to prove in all situations that expression going to give a truth value. So we are consider that one as a tautology. We are denoted by using these two symbols for contradiction and tautology. Some of the symbols we are using, just like premises we are using in a propositional logics are A, B, C, etc. Operation we are using in some propositional logics are unary operator and a binary operator. In a unary operator, negation symbol, that is not symbol we are using. In a binary operations, we are using a and symbol, or symbol, imply symbol, and a parenthesis using. The convention for using these operators in a propositional logic is negation. The unary operator not is binds more tightly than and or, and the and or symbol, and the and or symbol which are binds more tightly than the implication symbol, and the implication symbol is a right associative symbol one. Natural deduction is a collection of proof rules, premises, conclusions, sequence, and etc. The syntax which are using here, syntax, the sequence is some premises like 5 1 5 2 5 n, which are going to give some to validate the to prove which is true in some conditions, which is expressing like 5 is also true. Rules for a natural deduction. Rule for a conjunction. There are two rules for a conjunction: and an or and introduction and an or introduction. And introduction and elimination. This is our first rule, which is called as a rule for conjunction. Um, the first one, this is known as an introduction. It allows us to conclude phi conjunction with psi, given that we have already concluded that phi and psi are separately. This is, we can written it as phi and psi divides phi conjunction with the psi with the introduction of and symbol. The above line, above to this line is these are the two premises for this rule. Below this line goes to the conclusion part. So this is called as an and introduction. Here also the same thing. We are already concluded that phi and psi are going are true in some situations. So we can conclude the first rule. This is the first rule. It will says that if we have the proof of phi conjunction with the psi, then we are by applying this rule we can get the proof of phi. The rule E2 means conjunction elimination of elimination 2 says that same it allows to conclude these two. We are now we have the proof for phi conjunction with psi. We are going to conclude that psi is also true. Some of the example to prove P conjunction with Q and R, which are going to give the valid sequence like Q conjunction with R were valid. Here in the first line it shows that P conjunction with Q is the premises or given premise, sorry, and R is the given, and also R is the given premise, where Q, we are getting Q by eliminating the and conjunction on E2 on line 1. So we are getting Q. So after that combining introducing an conjunction symbol on line number 3 and line number 2, it will conclude that Q and Q conjunction with R. Rules for double negation. Double negation introduction. Here suppose we here there is no difference between the formula phi, this is the phi, and the double negation of psi, phi, which express no more and nothing less than phi itself. Suppose for example it is not true that it does not rhyme, it just more sentences like it rhymes. So this expression concluded this by like that we can eliminate the double negation by, suppose we have one symbol, one expression like a double negation of psi, some premise phi. We are eliminating the double negation from this given premise. We are concluded that phi is true. Example to here we are going to prove some one example which uses the double negation rule and the conjunction rule. Here the first P is the premise, double negation of Q conjunction R. This is also a given premise. So we have to conclude that these two are going to give double negation of P conjunction R. So for that we are introducing the double negation on line number 1, so it will give us to double negation of P. We are eliminating the double negation from the line number 2, that is the given premise. So we are getting Q conjunction with R. Here we get these two lines. We want double negation of P conjunction R, so we have to give eliminate the by applying their conjunction elimination on line number 4. We are getting R. So after this we are combining line number by introducing a conjunction symbol on line number 3 and line number 5. We are concluded that negation of double negation of P conjunction R is also valid. Rule for eliminating implication. There are two rules for eliminating implication: modus ponens and modus tollens. Here in modus ponens, here we have some sequence like 5 5 5, and we have another premise like phi implies to psi. Then we have to conclude that psi is also true for eliminating arrow elimination on this expression. Here considering some here we are considering one example like to prove that p p implies q and p implies q implies r is going to give r. These are the three premises given here. We have to conclude r. For that we are using arrow elimination on line number 1 and 3, so it will give rise to q conjunction q implication of r. After that we are eliminating by applying the modus ponens on the line number 2 and 3, it will give rise to q. So after that, by eliminating the arrow implication symbol on line number 4 and 5, it will give rise to r. So by using these three given premises, we are concluded that r is a valid. So this is the example sequence. Modus tollens. This is also one of the rule of eliminating an implication. Here we are having some expressions like suppose some expressions that p implies to q and negation of q are in the case. If p holds, we can use the arrow elimination to conclude that q also holds. We then have that q and negation of q holds, which is impossible. Therefore we may infer that p must be false. But this can mean that negation of p is also true. We summarize this reason into the modus tollens. This is as shown. This is the formula for modus tollens. Here considering an example, we are more familiar with the use of modus tollens, modus ponens and all. So here p implies q implies r, and p and negation of r are the three given premises here. We have to conclude that negation of q is also true. For that we are applying the arrow elimination on line number 1 and 2. It will give rise to q implies to r. By applying the modus tollens on line number 4 and 3, it will give rise to negation of q. The rule implies introduction. Here we have first of all by using here we are using this box. The reason is that we are assuming all assumptions are done here. Here we are assuming phi is true. After that, by suppose we are assuming phi, the premise of phi is true. By using that phi, we are concluded that psi is also true. For this within this box we are concluded that phi give rise to psi. So it implies that it introduces an implication symbol on phi and psi. Here I am considering an example to prove that negation of negation of q implies negation of p is valid. It going to give rise to p implies double negation of q. Here the given premise is negation of q and negation of p. This is the given premise. Here my assumption is p is true. So introducing a double negation on the given assumpted premise in line number 2, I am getting a double negation of p. By applying modus tollens on line number 1 and 3, I'm getting double negation of q. So our assumption is p is true. After that we are getting double negation is also true. So for this within this box we are concluded that p, this p is implies to double negation of q. That is arrow introduction, that is implies introduction on line number 2 to 4. Logical formula psi with the valid sequence phi are the theorems. Example of a theorem. Here this is also our assumption. Q give rise to R. Negation of Q implies negation of P is also our assumption. P is our assumption. So we are considering the assumption, 3 assumptions. So we are putting these 3 in a separate boxes. Here P is our assumption. Then after applying double negation, we are getting a double negation of P. By applying modus tollens on line number this 2 and 4, I'm getting a double negation of Q. After eliminating double negation on line number this 5, I'm getting a Q. After that implies elimination from line number 1 and line number 1 and line number 1 and 6, I'm getting R is true. After that within this box we are concluded that for this P assumption I'm getting a Q. For this reason I'm getting I'm concluded that P implies R, that is implies introduction from line number 3 to 7. Like that for the negation of P implies negation of negation of Q implies negation of P. For this I'm getting P implies Q. So I'm concluded that negation of Q implies negation of P implies negation of P implies R. That is arrow introduction on line number 2 to 8. In the last line, for the first assumption Q implies to R, and the last conclusion negation of Q implies negation of P implies R. This is we are introducing an R implication symbol on line number 1 to 9. It will give rise to this equation. This is known as a theorem. Natural deduction rules. In the natural deduction rules, we are constructing a proof structure. That is, this is the part of the structure of the formula. We are proved in this example. Here Q implies R. This is our first assumption. Negation of P implies negation of Q implies negation of R. This is also our second assumption. This is the first assumption, second assumption, and the third assumption. So we are putting it in a triangular boxes. These are the operations involved here. The part of the structure of the formula for the previously proved example to show that it determines the proof structure. This is the proof structure we are going to give. This is also true that this is by using Q implies R implies a negation of Q, negation of P, and implies Q P implies R is another theorem. To prove that some expressions like P implies Q implies R with a sequence, this is one theorem, and this is also one theorem. By applying some previously discussed rules, we are concluded that P implies Q implies R is going to be prove that P conjunction with Q implication R, and this is in vice versa. P conjunction Q implies R is going to give P conjunction implication Q implication of R. This is in the both the way we are concluded the formula. The proof for these two theorems are given here. The validity of these two expressions means that these two formulas are equivalent in the sense that we can prove one from another. We denoted by this these two by using this symbol. The rule for a distinction. Introduction of a distinction. This is the formula we are introducing. These are the two formulas for introducing the distinction. Here we have one valid premise phi. This phi is going to true means for any with any another premise it's going to true only. It's going to prove true only. For like that, suppose we have psi. We can conclude that psi and phi are true. Elimination of distinction. Suppose we have one proof like phi conjunction with q is true. In that we can conclude, we can prove that phi is our assumption and psi is also in our assumption. By using phi we can conclude that chi is our conclusion. By using psi also we can conclude that chi is our proof. For this we can by eliminating the distinction symbol on the phi and si, we can conclude that the chi is true. This is the valid the proof the sequence for expressing the validity of the some expressions. This is the given premise. This is our assumption p in conjunction q. We are going by assuming this is our assumption. P is also our assumption. By if P is true with some any other premise, it is P distinction with R is also true. Q is our assumption. We are going to give on eliminating applying elimination on line number 1 and 5. We are concluded P distinction R is true. Here P distinction R is in both the cases are true, so we are concluded that P distinction R that is by eliminating distinction symbol on line number 2, 3, 3 to 4 and 5 to 7, so we can conclude that P conjunction distinction Q implies P distinction R. The rules for negation. This is the suppose we have one expression with a contradiction and also we have by eliminating the contradiction symbol we are getting some premise phi. So this is known as a bottom elimination. In the not elimination, suppose we have one premise phi and another premise negation of phi, so we can conclude that these two are contradict to each other. So we are concluded that contradiction symbol they are contradict to each other. Introduction of a negation. These two are the previously discussed. These two are the elimination of negation. Here this one is the introduction of negation. Here suppose we are assuming some phi is our assumption. This one is true. After some applying some proof some rules, we are concluded that this one is contradict to our assumption, so which implies that our assumption is wrong, means it going to be negation of our assumption. This is known as introduction of negation. Rule for a natural deduction. In this we are continued the rule for a natural deduction. Here P implies Q and P implies the negation of Q, and with the sequence the negation of P is valid. This is going to give rise to the this proof. Some derived rules we are considering in a natural deduction are modest tolerance proof and double negation introduction rules and proof by contradiction and proof by LEM by proof by contradiction. Here by suppose we have phi give rise to psi with negation of psi, we are concluded that phi is negation of phi is true by applying modest tolerance. We know this rule in the previous slides, so this is the derivation for this rule. This is the derivation rule for double negation introduction. This is the proof by contradiction. That is our assumption. Basically, our assumption is negation, means false. After we are concluded that the false our assumption is also false. So false means it's going to give a true. So this is known as proof by contradiction. This is proof for LEM by applying a proof by contradiction. This is, thank you for giving this opportunity to introducing give this seminar. Thank you.